applications of linear algebra in machine learning, optimization, and compression. So neural networks depend on linear algebra. Now every layer in a neural network is matrix multiplication. So in a neural network, thinking is essentially a high speed relay race of matrix operations. Every time an AI processes a prompt or identifies an object, it is performing a massive chain of linear algebra. So every layer of a neural network makes use of an equation called y is equals to wx plus b, which involves matrix multiplication. Now let us decode this equation y is equals to wx plus b. So this single equation y is equals to wx plus b is the fundamental neuron logic used by everything from simple predictors to GPT-4. So in this equation, the W is the weight matrix. The W is the weight matrix. The weight matrix is the model's knowledge. The weight matrix represents the model's knowledge. So the idea is this weight matrix is basically a grid of numbers. It's a matrix. It's a grid of numbers representing the connection strengths. Now, this weight matrix is the one which the AI learns. So this weight matrix, it represents the AI's learned patterns. It is representing the model's knowledge which the AI has learned. So this is what the AI actually learns during training. If the AI is trying to recognize a circle, the numbers in W will be high for circular patterns and low for straight lines. So the numbers in this weight matrix, it is representing the connection strengths. It is representing a pattern which the neural network is trying to learn, which the AI is trying to learn. So when we multiply the weight matrix with inputs, if we multiply the weight matrix with the input vector, that is the x, you are essentially asking how well does this input match the patterns I have learned. So matrix multiplication of W with the vector x is basically equivalent to asking a question, how well does this match learned patterns? The idea is that the result of the multiplication of the weight matrix with the input vector, we compare it with the ground reality. And if it is close to the ground reality, it means the model's knowledge is appropriate. The model's knowledge is accurate. And if the multiplication of W with X is far away, if the difference between the predicted value and the actual value is large, it means the model's knowledge is not up to the mark. There is a need for more training. There is a need for more training. So that is the significance of the weight matrix W. So the result of the matrix multiplication of W with the input vector X will determine the accuracy of the model's knowledge. Now in this equation, we have small x, which is the weight, which is basically the input vector. So x is the input vector. It is the signal. So the incoming data, that incoming data can be raw pixels, word embeddings. So the incoming data into the layer. So in the first layer, this is the raw data. That can be pixels, audio frequencies, or word embeddings. In the later layers, it is the abstract features detected by the previous layers. Now, what is the role of this input vector? It provides the current state that needs to be processed. Now, in this linear equation, we have small b, which is the bias vector. So, small b, the bias vector, it is the threshold. So, bias vector is basically a list of numbers which are added after the multiplication. So the idea is that when we multiply the weight matrix with the input vector x, we add bias vector also. We add the values of the bias vector. So bias vector contains list of numbers that are added after the matrix multiplication. Bias allows the network to shift the activation function. So bias, it allows the network to shift the activation function. Even if the input Wx is 0, the bias ensures the neuron can still fire if necessary. So the idea is that if the product of Wx is 0, because of bias, the result will be some valid number, some positive number or some negative number. So this bias, it ensures neuron can fire even if Wx is 0. Bias provides the flexibility needed to fit complex data. So in this equation, y is equals to Wx plus b, b is the bias vector, list of numbers which are added to the result of the multiplication of w with the x. The bias vector, it ensures neuron can fire something even if the product Wx is 0. And bias, it provides flexibility needed to fit complex data. Then we have small y, which is the output vector. So small y is the output vector, which is the inside. So this is basically the result of the transformation. The result of the transformation, y. It becomes the input for the next layer. So the y becomes the input for the next layer. So now it's very clear to us that in a neural network, for every layer, like in every layer of a neural network, we will perform the operation y is equals to wx plus b. Now deep learning is basically a chain of transformations. Deep learning is basically a chain of transformations. So deep learning is called deep because it stacks many of these layers on top of each other. Mathematically, the deep learning, it looks something like this. So mathematically, the deep learning, it looks like y is equals to activation. So to make things easy, we start with the first, like w1 x plus b1. So in the first layer, we will calculate w1 x plus b1. The result, we are passing it in an activation function, and that result, we are multiplying it with the w2 plus the b2, because we know that the result of the first layer will be the input for the second layer. So the result of the first layer, we are multiplying it with the w2 and adding the b2 to it and passing it through an activation function, which will become the result of the second layer, which will become the input for the third layer, which we are multiplying it with a w3, adding it with b3 and passing it through the activation function and get the result. And if all the layers have been covered, then we will get the final input. So that is what a chain of transformation is. So in a deep learning, we have n layers. So in the first layer, we will be calculating the activation of wx plus b. The result will be the input for the second layer. There, once again, using this input, we will calculate w2 into this input plus b2 and passing through the activation function to get the result, which will be the input for the third layer. And like that, we will keep on doing until we get the final output. So that is what the deep learning is, a chain of transformations. Now in a deep learning, each layer takes the space defined by the data and wraps it. So in deep learning, actually in every layer, it is taking some data and applying some transformation to it. So the idea is that in deep learning, so this is the input. I call it the input vector. So in the first layer, I am directly passing the input vector, and the first layer will perform some transformations to it. The first layer might perform a rotation to find edges. And now whatever edges it found, it will pass it to the second layer, which will further perform some transformations to it. Let us suppose the second layer might perform scaling to identify shapes like the eyes, nose, wheels. Then we will pass that to the next layer, those shapes. Now the final layer might perform some sort of projections to squash all complex geometry into a single probability value. And the answer of the final layer is a number which is basically a probability, like 99% chance that the input is representing a cat. So this is how the deep learning works, layer by layer operation. And in every layer, we are using the same formula, y is equals to wx plus b. Now let us look at the computational reality. So in deep learning, because every layer is just a matrix operation, wx plus b, the entire field of AI hardware, like the NVIDIA GPUs and Google TPUs, is built specifically to do fused multiply add operations. So the AI hardware, the chips, they are built to perform fused multiply add operations. We call it FMA operations because we know that in deep learning, in every layer, we just have to compute this operation. We have to perform a matrix multiplication along with the addition. So fused multiply add operations. So these chips don't think in logic. They are massive engines designed to multiply and add matrices at the speed of electricity. So because of this linear algebra, because of this matrix computations, we can perform large scale operations in lightning speed. So that's the main idea. So the AI hardware, the GPUs by the NVIDIA, the TPUs by the Google, these AI hardware are built for FMA operations, fused multiply add operations. So these hardware, they don't think in logic, but they just multiply and add matrices at the speed of electricity. So that is the computational reality. So now we will look at the applications of linear algebra in optimization. So optimization and linear algebra. So see, basically AI, it learns by optimization. The goal of AI is to optimize, that is to minimize the loss function. Now let us see what role do linear algebra plays in optimization. Let us try to understand that. So training an AI model isn't a guess game. It is a high precision search through a multi-dimensional landscape. So basically in artificial intelligence, when we are training a model, we are finding the most optimal values for the parameters. If we fit those values, we will be able to minimize the loss. So training an AI model means a high precision search through a multi-dimensional landscape. And optimization is the process of finding the minimum, finding the lowest point, the minimum error in that landscape. And linear algebra provides the compass and the map. So linear algebra provides the tools needed to find the lowest point in that landscape. So training an AI model is basically a high precision search through a multi-dimensional landscape. Optimization is the process of finding the lowest point in that landscape. And linear algebra provides the compass, the map, the tools to find the lowest point. So that is the significance of linear algebra. So linear algebra provides us the tools through which we can perform optimization. Now let us look at AI training as math problem. Now let us look at AI training as a math problem. So when we train a AI model, we are trying to find the perfect values for the weight matrix. So training an AI model means finding the unknown weight matrix. The objective is to minimize the loss function. when we minimize the loss function, our prediction will be very close to the ground reality. Loss function is basically the mathematical difference between what the AI predicted and the ground truth. The mathematical difference between the prediction and the ground truth is the loss function. And our goal is to minimize the loss function. That is the objective. The scale. Now, basically, to minimize the loss function, we will be optimizing billions of parameters simultaneously. So, when we are training AI model, we will be optimizing billions of parameters simultaneously. And to do it, we cannot do it by hand. You will need a system of vectors to move the model towards accuracy. So we will be needing a system of vectors to move towards accuracy. So now it is very clear to us that training an AI model is like a high precision search through a multi-dimensional landscape. Optimization is the process of finding the lowest point in that landscape, and linear algebra provides the compass, the map, the tool to find the lowest point. Mathematically, training an AI model means finding the weight matrix, finding the perfect values for the weight matrix, which can minimize the loss function. So if we have found a perfect weight matrix, if we multiply it with the input vector, so whatever predictions we got, it will be very close to the real values, the ground values, the actual values. So that is the objective of training an AI model. The objective is to minimize the loss function. And thus, if we talk about the scale, when we are training an AI model, we are optimizing billions of parameters simultaneously. And to do that, we will be needing a system of vectors which will be moving towards accuracy. That is the idea. Now let us understand the tools the linear algebra provides to help us in optimization. So the linear algebra, it provides us the gradients. So the gradients are like compass. They show the direction. They show that in which direction should we move and how much we should move. So linear algebra provides gradients as tools. So the gradient is basically a vector of partial derivatives. In linear algebra terms, it points in the direction of the steepest slope of the error. So in terms of linear algebra, gradient, you can consider it to be a vector which is pointing to the steepest uphill slope. So the idea is that you are at a point. Now, from this point, in different directions, you might have different vectors with different steepness. So gradient is a vector which is pointing to the steepest uphill slope, like let us suppose this one. So if this is the steepest uphill slope, then this will be the gradient. Then I will be taking this direction. So gradient is a vector of partial derivatives which is pointing to the steepest uphill slope. Now to improve or to optimize the AI, it takes the negative gradient to move downhill because our goal is to minimize the loss. So the steepest uphill slope, we will move in a direction opposite to it. So we take the negative gradient to move downhill, and that is what the gradient descent is. Gradient descent means descending, moving down, the moving downhill in the direction of the gradient or opposite to the direction of the gradient. Now, without vectors, without this gradient, we could not calculate how 100 million weights interact to affect a single result. Because of this mathematical tool, because of this gradient, which is a vector of partial derivatives pointing to the steepest uphill slope, we can very easily find the direction in which we should move. So we take the negative gradient to move downhill, the gradient descent, and we get a direction which will take us to the lowest point in the landscape, which will minimize the error. So gradient is a very powerful tool which plays a role in optimization. Hessians, the curvature. So if the gradient tells you the direction, the Hessian tells you how fast the terrain is changing. Hessian is giving us the information about the curvature, how fast the terrain is changing. So gradient gives us the direction. Hessian tells us the speed of terrain change. So Hessian is a square matrix of second order partial derivatives. So Hessian is also a matrix. Like Hessian is a matrix. It's a square matrix of second order partial derivatives. So Hessian matrix helps the optimizer understand if it is in a wide flat valley where it can take big steps. So Hessian information, like Hessian matrix will give us an information whether we are stuck in a wide flat valley wherein the speed of terrain change will be very less, or we are in a narrow steep canyon where we have to take the careful steps because the speed of terrain change is extremely high, the curvature we can see. And because of this Hessians, we can determine when to take big steps and when to take small steps. Because gradient is telling us the direction and we know that, okay, we know that we have to move in this direction. But if we take big steps, we might miss the lowest point. We might miss the minima. We can overshoot it. That might happen. So Hessian will give us an idea. The curvature will give us an idea that how big steps should we take. If the speed of terrain change is very less, then we can take big steps. But once we are getting higher values of Hessian, the speed of terrain change is high, then we have to take small steps. Careful steps we have to take. So this Hessians is the basis for advanced second order optimization algorithms. Now the next tool of linear algebra which plays a role in optimization is the least squares. So least squares is the shortcut. So the idea is that sometimes we don't need to search for the best answer. We can calculate it directly. And let us see how we can calculate the best answer directly. Rather than searching for the best answer, we can calculate it directly. So in linear regression, the least squares method finds the point where the error vector is perpendicular or orthogonal to the data space. So in regression, we use the concept of projection. Projection means finding the points where the error vector is perpendicular to the data space. So now let us suppose this line is representing the data space and this is the point. Now the distance of this red point from the blue line is the error and the error vector is this, and the perpendicular of this point is this. Let me draw it with a green pen or orange pen to make it visible. So this is the idea. So in regression, if we just solve this equation, A transpose AX is equals to A transpose B, the linear algebra will find the single best fit in one shot. So no need to do any gradient descent or search. Just solve this equation to get the single best fit. So that is the least squares method. So in least squares, it's a tool of linear algebra. Using it, we can calculate the best answer rather than finding for it. So we just have to solve this linear algebra equation A transpose AX is equals to A transpose B to get the single best answer. So the next important tool of linear algebra which plays a role in optimization is the projections. So projections means simplifying the search. So high dimensional optimization is low. So high dimensional optimization means we are having various features, high dimensional space, like lots of features we have. Now optimization will be slow. If we have lots of features, the optimization will be slow. So in high dimensional spaces, the optimization is slow. So high dimensional optimization is slow. Projections allows us to simplify the problem. And let us see how. So the idea is that by projecting a complex high dimensional error surface onto a low dimensional subspace. So if we can transform a high dimensional error surface to a low dimensional subspace, if we can reduce the dimensions, we can find a good enough solution much faster. And this is what we do in stochastic gradient descent. So this is vital for stochastic gradient descent, which looks at small batches of data at a time. So rather than exploring the entire data set, we are just exploring small batches of data. So that is what stochastic gradient descent. So the idea is very clear that using the concept of projections, we can simplify the search. Idea is that if we project a complex high dimensional error surface onto a low dimensional subspace, we can simplify the search. We can perform the search much faster. So we saw the tools linear algebra provides for optimization, like the gradients, the Hessians, the least squares, and the projections. Now let us discuss the chain rule and backpropagation. Now one very interesting question we have, like how does the output mistake tell a neuron at the input to change? So the idea is that, see, in a neural network, what we do, we start with some random weights, and using those random weights, we perform some matrix operations in every layer. In every layer, we will calculate y is equals to wx plus b. And in this way, at the final layer, we will get the output. And we match or we compare that output with the ground reality, the actual result. And the difference is the loss. Now, let us suppose our output was a very big mistake. It is very far away from the actual value. It means our neural network made a mistake. It means whatever the initial guesswork we did, whatever weights we guessed, they were wrong. Now a very big question is how we will update the weights so that we can minimize the loss. How we can update the weights so that in the next turn our output will be closer to the actual output or the ground reality. So that is the idea. So that is what the chain rule and the back propagation is. So what we do is we go for matrix transpose. So what we do is that whatever the error we got, the difference between the predicted value and the actual ground reality, we will send it backward. So during the training, the error is sent backward through the network. This involves multiplying the error vector by the transpose of the weight matrix. So that is what the back propagation is. So whatever the error was, we will send the error backward through the network, and in every layer we are multiplying the error vector by the transpose of the weight matrices. If we talk about linear flow, so linear algebra allows the blame for an error to flow perfectly across millions of connections, ensuring every single parameter is adjusted by exactly the right amount. Because of this back propagation, the linear algebra is allowing the blame for an error, like the whatever the error is, it is propagating from the backward direction. It is flowing perfectly across millions of connections, ensuring every single parameter is adjusted by exactly the right amount. So that's the idea of backpropagation. So now in this way, the weights they get updated, the parameters they get updated because whatever the error we got, we send it from the backward direction to all the connections. And in this way, the weights of the connections they get adjusted. And then we do the forward pass. In the next forward pass, the output will be close to the actual output, the ground reality. And once again, whatever error we got, we will back propagate it to update the weights. And we keep doing it until our predicted value is very close to the real value. And this is how a neural network or a deep learning it works. So basically, in a neural network, we have the learning loop. So there is a forward pass wherein we start with some random weights. In every layer, we calculate Wx plus B. The output is sent to the next layer. Like that, we perform operations and we get the final prediction. Then we will calculate the error. We will compare the output vector with the target vector, which is the ground reality vector, the actual vector. And the difference is the error. We calculate the error and then we optimize it. To optimize it, we use gradients, which are vectors, which will tell us the direction, in which direction should we move. And we have Hessians, which will give us the idea about the curvature, like how big the step should be to update the weights. So gradient will tell us whether we should increase the weight or decrease the weight, and Hessian will tell us the amount, whether the update should be a big update or a small update. And once we optimize it, and for optimization, we make use of the back propagation. So the error vector, we propagate it from the backward direction and we update all the weights. And once the weights are updated, we once again go for a forward pass. Now we have a updated weight matrix. So when we go for a forward pass, the final prediction will be a bit different and it will be bit closer to the target, to the actual input, the actual value. And once again, we'll calculate the error, optimize it, and we will keep on repeating it billions of times until the error is close to zero. And this is how the learning loop, this is what the learning loop is. Now let us discuss the application of linear algebra in data compression. So data compression and linear algebra. So what role does linear algebra plays in data compression? So first let us understand the meaning of data compression. Like what do we mean by compressing information? So data compression is the art of finding the essential part of a matrix and throwing the rest away. So data compression is basically the art of finding the essential part of a matrix and throwing the rest away. Now, in linear algebra, this technique or this process is called low rank approximation. And it's how we move massive amounts of data across the internet without breaking it. So what we do is that we compress the data and then we send it to the network. So low rank approximation is how we move massive amounts of data across the internet without breaking it. So data compression is very clear. Data compression is the art of finding the essential part of a matrix, throwing the rest away. And we make use of a technique of linear algebra called low rank approximation to do it. Now, if we talk about the master tool for data compression, so singular value decomposition, SVD. So singular value decomposition is the master tool. So you can call it like single value decomposition as the Swiss Army knife of data science. So SVD, it takes any matrix A and breaks it into three specific parts. So that is what the singular value decomposition. So we break a matrix into three parts: U, sigma, V transpose. So here U and V are the directions of pattern in your data. So this U and V matrices, they tell you the directions of the patterns in your data. And sigma, it is a diagonal matrix of singular values. And these singular values are ranked from largest to smallest, representing the importance of each pattern. So in a singular value decomposition, we decompose any matrix A into three components or three parts: U, sigma, V transpose. U and V represents the directions of patterns in your data, and sigma is basically a diagonal matrix of singular values which are ranked from largest to smallest, representing the importance of each pattern. Now, how exactly we compress the data? Like how SVD compresses the data. So to compress data, you simply truncate the matrix. Like you keep only the top few singular values and discard the tiny ones. And with this, we are capturing 90% of the information using only 5% of the storage. So now the idea is very clear, like how we do data compression. We make use of a technique of linear algebra, that is the singular value decomposition, wherein the matrix containing the data, we break it into three parts, and the sigma is a diagonal matrix of singular values which are ranked in largest to smallest. So the only the top few singular values we will consider, and all other values we can truncate, we can discard it. In this way, we are retaining 90% of the information using 5% of the storage. So that is how the data compression plays a role. Like we are not going very deep, we are just getting an idea. And definitely you can explore it, you can go very deep and find out exactly how it is working. But I gave you an idea. Now let us look at some real world applications of data compression. So data compression do play a role in JPEG and video streaming. Visual redundancy. So the idea is that, see, images are matrices where nearby pixels are usually very similar, because in images nearby pixels are very similar. So what we do, how we compress it, instead of storing every single pixel, we use linear transformations like the discrete cosine transform to identify the frequencies of the image. We keep the low frequency data, that are shapes and colors, and discard the high frequency noise that the human eye can't see anyway. So the idea is very clear that how we do the data compression in JPG and video streaming. We perform linear transformation, and we make use of something called as discrete cosine transform, which will identify the frequencies. And once the frequencies are identified, we will keep the low frequency data like the shapes and colors, and we will discard the high frequency noise which human eyes can't see even. And in this way, if we are eliminating some high frequency noises, we are compressing the size. And this is one of the reason a Netflix stream, it looks clear even on a slow connection. Now the second real world application is image denoising, cleaning the matrix. So see, noise, if we talk about noise in a photo, is just random, small values scattered across the matrix. So noise is something unwanted. So noise is some random small values which are scattered across the matrix, and we have to get rid of the noise. And how we can get rid of the noise? When we perform the singular value decomposition SVD, the clean image is represented by the large singular values, while the noise lives in the tiny ones. By zeroing out the small singular values and reconstructing the matrix, the noise, it disappears. and we are able to perform image denoising. And with image denoising, since we are removing the noise, we are compressing the image, and we are making use of a linear algebra technique, that is the SVD, Singular Value Decomposition. Now the next real world application of data compression is the principal component analysis, PCA. So reducing the number of variables in a data sets, like reducing from 50 health metrics to 3 health scores, is what the principal component analysis is. Now principal component analysis, it uses the same logic as the singular value decomposition to find the principal components, the eigenvectors of covariance matrix. It projects the high dimensional data onto a best fit plane, preserving the maximum amount of variance. So principal component analysis, what it does is that whatever data we have, first we calculate the covariance matrix of it, and using it we determine the eigenvectors and eigenvalues. And then we will basically transform the features into, like 50 features, we can transform it into 6 to 7 features. And out of that, only top 3 or 4 features will be relevant, containing the maximum amount of information, preserving the variance. And we just make use of that. So in this way, we are eliminating unnecessary features. And the next real world application is the latent semantic analysis, understanding text. So how does a computer know that doctor and physician are related? Because doctor and physician, they are related terms. Both are talking about something similar. So we create a term document matrix where rows are words and columns are books. By applying the singular value decomposition to this matrix, we collapse thousands of words into a few concepts. We call it the latent topics. Even if two documents don't share the exact same words, their vectors will point in the same direction in this concept space. So the idea is we start with a term document matrix and we perform the singular value decomposition of that matrix, wherein we collapse the words into concepts, the latent topics, where vectors will point in the same direction in this concept space. Now let us look at the why behind the math. See, if there was no compression via linear algebra, like without linear algebra compression, things would be very different. Phones would run out of storage. AI models would be too large to fit into computer memory. The internet would be unusable for video or high resolution images. So everywhere data compression do play a role, and linear algebra is powering the data compression. So linear algebra data compression has got some serious applications, some serious real world applications. So linear algebra, it allows us to treat data not as a collection of bits, but as a geometric shape that can be simplified without losing its soul. So linear algebra treats data as a geometric shape that can be simplified without losing the information, losing its soul. Now let us discuss core mental model. So if we talk about data, data is the sum of geometry, which is the patterns, the algebra, some mathematical techniques, and the computations. So data is the sum total of geometry, algebra, and computation. So the core mental model is the realization that data is just not a list of numbers. Data is not just a list of numbers, but data is a shape that can be moved, that can be measured, and that can be calculated. So data is not just a list of numbers, rather data is a shape, it is a pattern which can be transformed, which can be moved, which can be measured, and which can be calculated. By merging these three pillars, the geometry, the algebra, and the computation, linear algebra, it transforms abstract information into actionable intelligence. Now let us understand these three pillars in some detail. So let us first try to understand data as geometry. So data is equals to geometry is the where, and this pillar, data as geometry, provides us the intuition. It allows us to visualize complex data sets as physical space. So rather than treating data as just list of numbers, if we treat data as vectors, then we are able to visualize the complex data sets as physical space. So space and distance. Every row in a data set is a point in a multidimensional space. If 2 points are close together, they are similar. So if we treat data as a geometry, then every data point will be a point in a space. And if they are close, if the distance between the points are less, it means they are similar. So closeness means similarity. So that is the advantage we get if we treat data as a geometry. Using the space and distance, we can find are they similar? Direction. Vectors tells us which way the data is pointing. So vectors, they show the pointing. In AI, a word vector for king minus man plus women points directly toward the vector for queen. So what we are doing is that we are starting with a king vector, we are subtracting man from it and adding a woman. So we are talking about a women king. So women king is a queen. So we are heading towards the queen vector. So such kind of an operations we can perform if we treat data as a geometry, because data as a geometry means we are treating data as not just as a list of numbers, but rather as vectors and matrices, the shape of data. So if we treat data as geometry, we use this geometry to find the manifold, the underlying surface that the data lives on, allowing us to ignore the empty space and focus on the patterns. So now it's very clear that if we treat data as geometry, like data is equals to geometry. So if the data is treated in the form of or represented in the form of vectors and matrices, then it will give us some special intuition. We will be able to decode the where, like in a multi-dimensional space, the data points, the distance between the data points will give us an idea about the similarity, whether the two data points are similar. The directions, the vectors, they will help us to perform some operations on it to head towards a vector which we are seeking. And with data geometry, we can just focus on the manifold, like the underlying surfaces where the data lives on, eliminating the empty spaces or ignoring the empty spaces and just focusing on the patterns. Now let us see data is equal to algebra, the how. So it is all about the logic. Now once we represented the data, now let us suppose we have to perform some operations. How we can do that? What logic should we apply? That is what data is equals to algebra. So here we are talking about transformations. How we can transform data. So algebra, it allows us to wrap the space. If the geometry is too messy to understand, we use a matrix algebra to rotate or stretch it until the pattern becomes clear. So once we represented the data, if we see that the representation is very messy, we can perform some operations on it. We can scale it, we can compress it, we can rotate it so that we get some clear patterns. So let us suppose this is what the representation is. We can apply some linear algebraic transformations to get clear patterns which we can analyze. Now, if we talk about data is equals to algebra, we have relationships. Algebra allows us to define how variables interact. So algebra, it defines the interactions. It turns a feeling about a trend into a rigorous system of equations that can be solved. So with algebra, we can define the interactions and we can turn the interactions, the relationships into system of equations which we can solve and the invariance. So algebra helps us finding things that don't change, that are invariant, like the eigenvalues. This is how facial recognition works. It finds the algebraic properties of a face that stays the same even if the person is in different lightning or a different angle. Because let us suppose the person, if he goes to a different lightning condition, there are many patterns, there are many features which will remain identical. And that is what invariance is. And algebra helps us to find those features which remain invariant, which does not change. And that's the power of algebra. Data is equals to algebra. So the idea is that once we represented the data, we can apply transformations on it to make the patterns more clear, more visible. We can identify the relationship and we can solve some rigorous system of equations to find the relationship, to find the interactions between the variables. And we can also find the features, the parameters which does not change, which stay invariant. So that is what data is equals to algebra. Then we have data is equals to computation, the scale, the power. So when we are talking about computation, parallelism. So unlike calculus or standard logic, which often happens step by step, linear algebra is massively parallel. You can multiply a row and a column independently, independent operations. So simultaneous operations, billions of simultaneous operations we can carry out. So linear algebra, unlike the calculus or standard logic, is massively parallel in nature. Hardware, the hardware optimization. Because the math is so structured, it makes use of matrices, vectors, the grid of numbers. Engineers, they built GPUs and TPUs specifically to do nothing but matrix multiplication. So the core idea behind the GPUs and TPUs is the matrix multiplication. Like GPUs and TPUs, they can perform billions of simultaneous matrix multiplications. And we have efficiency. Modern algorithms like the BLASH can handle matrices with trillions of entries. So this allows us to scale from toy problems to global scale systems like the Google search or the ChatGPT. So the idea is very clear, like data is equals to computation. So now the data we are dealing with, because of linear algebra, we are representing the data in the form of vectors and matrices. Because of that, our data will become massively parallel and our data is optimized for GPUs and TPUs, wherein billions of simultaneous matrix multiplications can be performed and our data will be efficient. It can be scaled to trillions of entries and we can transform from toy problem to global scale systems. Now let us look at the synthesis, how they power AI. Like if we combine all this together, so modern AI is the perfect intersection of these three pillars, the geometry, the algebra, and the computation. So the geometric intuition tells the researcher, I want to group similar concepts together in a 512 dimensional space. So group concepts in 512 dimensional space. The algebraic equations like the Wx is equals to B tells the model use this specific matrix multiplication like Wx plus B to move the data there. So using geometric intuition, we were able to group concepts in a 512 dimensional space. Using algebraic equations, we did some kind of a processing. We did some kind of a matrix multiplication to move the data in that space. And computational efficiency tells the hardware do these 100 billion multiplications in less than a second. And with computational efficiency, the operations, the algebraic operations, we were able to carry out efficiently in fraction of seconds. So now it's very clear that how these three pillars, the geometry, the algebra, and the computation, they are powering the AI. So if we are representing the data in the form of vectors and matrices, we are able to group it in a way we want. We can group similar concepts, group concepts in any n-dimensional space. By applying the algebraic equations, we can transform it, we can move or change that space, move the data there. And computational efficiency, it allows us to perform operations in an efficient manner in fractions of seconds. So overall, the result is a system. We get a system that can understand language, a system that can see objects, and a system that can predict the future, all by treating reality as a massive computable geometric grid. So if we consider data is equals to geometry plus algebra plus computation, we can treat reality as a massive computable geometric grid wherein our system can understand, it can see objects, and it can predict the future. Now let us discuss the most important skill. So the most important skill is to learn to think in vectors and matrices. So we have to transform a real world problem into a matrix problem. We have to learn to think in terms of vectors and matrices. This is the most important skill. Thinking in terms of vectors and matrices is the superpower that separates someone who merely uses AI tools from someone who can architect them. So if you are someone who will be building the AI models, who will be building AI, then you have to think in terms of vectors and matrices. Thinking in terms of vectors and matrices is the superpower. It is the most important skill. It's a shift from seeing data as individual points to seeing it as a fields of influence and geometric structures. So if you think in terms of vectors and matrices, then you're shifting from seeing data from individual points to seeing the data as fields of influence and geometric structures. Now let us look at like how experts in different fields, they apply this mental framework of thinking in terms of vectors and matrices to solve world-class problems. So if I talk about thinking in vector spaces, the context skill. So experts don't see a word or an image, they see a coordinate. So the mindset is don't look at an isolated data point, rather think of it like a coordinate in a n-dimensional space. So the definition, so the mindset is if you are building an LLM, you don't think about definitions. You think about where a word sits in a 1536 dimensional space or where the word sits in a high dimensional space. So the idea is the mindset is when we talk about vector spaces, we are not at all looking at the values, the data, or the definitions. Rather, we are thinking in terms of coordinates, like where the data will sit in a high dimensional space. So that is the mindset. And the skill we get if we think the data or if we visualize the data in terms of a vector space, what benefit we will get is we can make use of the distance and angles. And we can make use of the distance and angle to find the related data points. So an expert knows that if two vectors have a high cosine similarity, then they are pointing in the same direction, regardless of the spelling. The underlying concepts are related, regardless of how they are spelled. That's the idea. So if we consider the data, or if we think the data in terms of vector spaces, then we are not talking about the numbers, we're not talking about the definitions, but we are considering the coordinates. Like we are talking about where the data is sitting in high dimensional space. We can make use of distance and angles to calculate cosine similarity. And if two vectors have high cosine similarity, it means they are related. So it means we are talking about related concepts regardless of the spelling. Thinking in terms of matrix transformations, the action skill. So matrix transformation is the action skill. So in robotics and computer vision, experts don't think about moving an arm or rotating a photo. They think about wrapping space. So a robot arm moving from point A to point B is just a series of matrix multiplications. So the idea is if we think in terms of matrix transformation, then any operation, any action, we treat it like a series of matrix operations. And in this way, we are visualizing the basis change. An expert can see how multiplying a vector by a matrix changes the camera view or the coordinate system, allowing the robot to understand where its hand is relative to the cup. So, if we think in terms of matrix transformation, we are actually visualizing the basis change. Mathematically, we are able to determine how much we changed or how exactly the robotic arm moved relative to the any object. So we have to think in terms of matrix transformations. Any action, we have to think in terms of matrix transformations. Thinking in terms of projections, the simplification skill. Optimization and data science experts, they are masters of shadows. So real world data has too much noise. An expert asks, what is the 2D shadow of this 100 dimensional problem? So that is what the simplification scale is. So we should think in terms of projection. So the idea is that high dimensional problem, we have to convert it into a low dimensional problem. So that is what the dimensionality reduction is. So here we are talking about the dimensionality reduction. So we should think in terms of projection. And the skill for that is dimensionality reduction. We should strip away junk. Make use of projection to strip away the junk variables, leaving only the principal components that actually drive the results. And then we have thinking in terms of decompositions, the diagnostic skill. So how we can think in terms of decomposition. So first let us understand what is the meaning of it. Thinking in terms of decomposition. So this is the highest level of thinking, taking a complex, messy system and breaking it into its pure mathematical DNA. So thinking in terms of decomposition means a massive matrix of user data, we break it into a combination of simpler hidden patterns. So massive matrix is equals to combination of simpler hidden patterns. So we decompose a messy system into pure mathematical DNA, smaller matrices. So that is what the decomposition, thinking in terms of decomposition. Now the skill for that is the singular value decomposition or the eigen decomposition. We can look at an expert looks at a confusing matrix and thinks what are the eigen vectors, the fundamental directions, and the eigen values, the strength of those directions of the system. And using this information, they break the complex system into smaller subsystems. That is what the thinking in decomposition is. So now it's very clear that we should think in terms of vector spaces. So here we are talking about the context skill, and distance and angles are the tools for us. We should think in terms of matrix transformations, the action skill, and the tool is to visualize the basis change. We should think in terms of projection, the simplification skill. The tool is to do the dimensionality reduction. We should think in terms of decomposition, the diagnostic skill. The tool is singular value decomposition, principal component analysis, or the eigen decomposition. Now, let us get a realization why thinking in terms of vectors and matrices is the most important skill, why it is the superpower. So, see, if you only know the code, you are a passenger. But if you think in linear algebra, you are a navigator. So, you see, the idea is that if we just focus on the code, we are just a passenger. Passenger means we don't know what is happening, how the system is working, or how the driver is driving the vehicle. If we just know the code, we are just calling some inbuilt functions. We don't know what is happening in that inbuilt functions. But if you think in terms of linear algebra, then you are the navigator. You will be designing those inbuilt functions. You will be leading that in which direction should we move. You will become the navigator. So why thinking in terms of vectors and matrices is important? It is important for debugging. Let us suppose a model fails. When a model fails, you don't just try more data. Rather, you will look at the rank of your matrix to see if your data is redundant. Scaling. You understand why a GPU is fast and how to structure your math to take advantage of it. Because if you think in terms of vectors and matrices, you have got the in-depth knowledge of how exactly the model is working. You can debug the model, you can scale it, you can make the efficient use of the GPU. You know that you have to convert the problem into the matrix problem because GPU is made for matrix multiplication. You can structure math for GPUs and the innovation. Every major breakthrough in AI, like the transformer architecture used in ChatGPT, was born from someone finding a new way to multiply and attend to matrices. So any innovation will be in terms of vectors and matrices. So now it's very clear to us the importance of thinking in terms of vectors and matrices. We can get to know how the model is working. We can debug, we can scale, and we can innovate our model. So if we can summarize this, the expert's fluency. So in traditional thinking, we say like if price goes up, sales go down. But in vector and matrix thinking, the same statement we say that negative correlation vector in feature space. Because if one feature is increasing, the other is going down, it is a negative correlation. In traditional thinking, if we make statements like rotate image 90-degree, in vector and matrix thinking, we say apply rotation matrix to the pixel grid. In the traditional thinking, if we say the statement like find the most important factor, in vector and matrix thinking, we say find the eigenvector with the largest eigenvalue. Now let us look at some real world examples where linear algebra appears daily. So we will look at the application, the linear algebra tool, and the connection. So if we talk about the Google search, application is the Google search. Now Google search, it makes use of eigenvectors in its page ranking algorithm. So how does importance relate to vector direction? Now if we talk about the application of face recognition, in face recognition, we make use of the principal component analysis. wherein we reduce the complex faces to essential eigenfaces. In the ChatGPT embeddings application, we make use of the vectors, semantic space. So we represent the words as vectors as points in the high dimensional space. In the Spotify recommendations application, we make use of matrix factorization, the collaborative filtering. We decompose the user item matrix to find hidden patterns. In image filters, we make use of the linear algebra tool called the convolutions, kernels and matrices. So in convolutions, we slide a small matrix over an image and we perform some specific operations like we detect edges, blur, and the next application is the robotics. So in robotics, we make use of transformations. The linear algebra tool is the transformations like the matrices and the kinematics. So moving robot arms use rotation and translation matrices. So these are like some real world examples where linear algebra appears daily.